Well, thank you again for nice presentations on Friday, and hope your weekend was relaxing enough to accumulate energy. Also hope you're doing well with your other classes. So about now we will start little homeworks, and you see, you probably saw the first one. It's like nothing to do. It's high school level. So if you practiced products, transformations of sines and cosines, you'll do it quickly. Later, we will ramp up with a little bit more time-consuming homeworks, but I hate them, and I'll try to minimize the effort because I was in your skin for a long time. So we are in the physical chemistry course. We want to interpret and predict outcomes of the instrumental measurements to characterize materials, and I was feeding you these promises for long enough that we will go to practical applications, but probably starting next time. Now we need one more dry abstract theoretical thing, but I will not promise that we'll stop new theories, but it will be kind of marker. So after today's theory, you have a minimalistic level of background to do applications for sure. And the thing that we're going to cover today will be a replacement of the evolution iterator. So on our journey to get concepts, to get background and formulate Schrödinger equation, evolution iterator was quite useful concept. I hope so. But and in our projects in the meta later on, you also will play with evolution iterator. But generally, it is. Oh, I don't tell you. So generally, evolution iterator is very untreatable for pen and paper solutions for theories, because it's like more integral equations rather than differential equations. And if you had differential equations, maybe there was a one section there about integral equations which are less developed, because there are less standard ways to solve them. And if one goes for numerical solutions, the evolution operator is also not as comfortable as Schrödinger equation, because it cannot be reduced to eigenstate problem. So we are going to do something that is based on eigenstate problem, but which replaces evolution operator technique and predicts future for the wave function. So does it look reasonable as a general goal for the meeting? So you have an idea what we're talking about. Okay. Hello, Mike. Hello, Ellison. Thank you for connecting. Let me know if you do not hear. If you do not say or type anything, I'll assume that you hear well. Okay. So let's focus on slides. So here is a little plan of where we are, and I got tired updating this table from year to year, but we see the plan. We swapped 8 and 7, so we did presentations on postulates, and we do last thing in the chapter of fundamentals. And then there will be a chapter on uncertainty, where we will consider free electron in space. Then there will be electron confined in a box, which is kind of oversimplification of a molecule. Then there will be oscillations, and then angular momentum and presentations. And in angular momentum, I will cover hydrogen atom and like SPD orbitals, and also some like rotational spectroscopy. So it's not perfectly covering everything one can do, but it will lay foundation. foundations. And if anyone wishes, things are recorded from previous years, one can look, and I'm not sure if I'm doing anything better. So so here's the homework that I suggest we do by Friday. So try to either send as an email attachment or bring printed version into the class. And let me know if there are any challenges. I think it is much less than we covered in the class. So here is the summary slide. Hello, Nate. Good morning. How are you? So my goal is to arrive to the slide and be happy. So let's look at it and discuss, and then if time allows, I'll provide derivations to justify it. So here are the things that we used to accept, and if we really would, if everyone here would like to go into more classical style of education, maybe one should make a quiz or examine the equation. But I hope it's clear enough, and you do not need to play this childish game, so you get some impression what it is. So there are ways to predict the future. We have wave function in the initial time. We can get wave function in the final time by applying evolution to this yellow box. Or if the time increment is really small, we can replace this evolution operator by 1 minus Hamiltonian times delta t, which can be derived either from Schrödinger time-dependent Schrödinger equation, or just by expanding this exponential into power series and dropping higher terms. Right? We see benefits of the first equation, that initial and final time can be as far from each other as we want. And the price is that it is operator matrix in the power of exponential. Make things bright. So it is mathematically uncomfortable. This thing mathematically is very comfortable. Like it is either function, this is differential operator, or this is vector and this is matrix. So it's a very basic operation. But the limitation is that we can predict only very near future. If we will use longer time, then it will be not a good representation of exponential, and the results will be unacceptable. It will be big error. So we want something that is as cheap as second, but as general as first. And in order to get to this third way, we need the foundation that we covered through your presentations and through lecture before that. So time dependent and time independent Schrödinger equation. So suppose that we have a system for which total energy operator is known, and very soon, as we start applications, you will see that you already know from your presentations, and you probably suspect it from common sense, that for each molecule there is its own total energy operator, right? So suppose we have an object that we want to describe. We have the Hamiltonian operator. Then let's suppose that we have solved time independent Schrödinger equation. So which information does it give? So what do you learn from solution of time independent Schrödinger equation? Anyone is welcome to speak, and I will personally ask for. Like if, I'll tell some colloquial language that only all of you understand. If you find if you run single point DFT, what are you getting? How many? Total energy, and you get orbitals, right? So how many energies and how many orbitals? More than one.
Yeah, more than one definitely.
Okay. So and Schrödinger equation is the same. Energies and orbitals. Now, repeating question to everyone: what do we get if you solve time-independent Schrödinger equation? What?
Energy and orbitals.
Okay. And how do we call orbitals in this course?
Energy.
Energies are there. Okay. Eigenenergies, eigenstates, eigenfunctions, wave functions. So which letter do we may use for this eigenfunctions?
Capital E.
No, for energy, capital E, like E for energy.
Okay.
One of my colleagues was developing a lecture for freshman chemistry without proper rest, and then let's consider iron, which is abbreviated as IR. So, but here it is a simpler situation. We have energy and it is letter E, and we function letter phi, which is like a circle, closed phi, right, for time independent. And if we want to be explicit, if we put brackets with arguments, it will have only x or x, y, z if it is three-dimensional, right? So it is right. Phi sub k is wave function, and E sub k is energy. So it's same like energies and orbitals, right? So by solving time independent Schrödinger equation, we have set of this data. And our goal, again, is to project past into the future. So let's suppose we do have wave function of the past. And like instead of past time initial, we can tell just 0, time equals 0. Then we are going to perform an operation of so-called convolution. We are going to multiply, notations. What's the difference of phi and psi? And I'm not the one or this class is not the one who place where this difference is, where this abbreviation is used. So it's quite common in most of the textbooks. So what is your guess about the difference between phi and psi? What are the arguments?
Phi is dependent on position and psi is dependent on both time and position.
Exactly. So time dependent, time independent, right? And some lazy people like myself often like to skip brackets because it's 3 symbols and here only 2. Just save time and write less. So, but under 5, one typically understands time independent. So, from previous considerations, we have suspicion that people like multiplying wave functions by itself. Wave function with star by wave function without star, right? So if one practices this multiplication of the eigenfunction and the function of a past, integral of a function should give a number. And there will be a number which will depend on the index of eigenfunction. Now, this number will serve as an input for this dark yellow box. And it tells that wave function of the future equals this C sub k, which inherits information about the past, times time independent eigenfunctions, times exponential accumulation of phase. So is it reasonable? Is it completely nonsense, or you don't care? So majority thinks it is yes, don't care. Very opposed. Okay, don't care. What about you? Not quite. Okay, so then I'm justified to stay here and mumble something else. Otherwise, if everyone would say yes, then we don't need the rest of the lecture. So my only goal in the remaining whatever 40 or 30 minutes is just to explain why and how we need this stuff. But if this protocol is fulfilled, then one can take the wave function of the past as an input and get wave function of the future as an output. And since this protocol relates to integrals, summations, and finding eigenstates, those are all standard procedures of linear algebra. And they are solvable either by pen and paper or by computers in much more efficient way than propagation by this exponential. So why do we need multiplied? Why do we accumulate phase with different pace? Is my task to talk about. So here is something that you probably remember, right? So time dependent, time independent set of wave functions, for some people call them orbitals, and energies. And if we take the same phi and multiply, it will be 1. If we have different, it will be 0. So this I will appeal to this little property, and it is often called orthogonal. Did you hear the word orthogonal in the past? Can you explain it by 2 fingers? What is it? What? Yes. Perpendicular, right? So a scalar product of 2 orthogonal vectors is 0. Scalar product of 2 collinear vectors is 1. So same thing is here. So the only difference is that the wave functions are also vectors, but in many infinite number of dimensions. But if they coincide, it's 1. If not coincide, 0. I do have strength to correct my ugly writing, but probably I will compensate it by explanation. So once upon a time, we were converting time dependent Schrödinger equation into time independent. And on this path, we were using separation of variables. So we assumed, and actually I never proved it, or I never referred you to a proof, but it's not our goal right now, that it's possible to separate variables. So we assume that this time-dependent wave function can be represented as a product or summation of products. And in general, so we found that time dependence is exponential with time in the power. And I don't quite remember if I proved it, or maybe I quickly showed and we all have already forgotten, but in fact, the power in front of this exponential for time dependent part is equal to the energy that comes from Schrödinger equation. Did I show it? Or I didn't, or I showed it, we all have forgotten? Maybe. If I didn't, I may show it once again. It's all consistent thing. If you just carefully convert from time dependent to time independent, this thing pops up. Now, the phi, this eigen wave functions, they are used as a product. So basically, we multiply wave function by this exponential, and it will be a solution. Can you help me by teaching me a little bit more about the differential equations? I remember that like about half or more than half of the class were taken. What's a for ordinary O point, D point, E, ordinary differential equations, linear. There are 2 concepts: general solution and partial solution. So will you please teach me, refresh my memory, what are their differences? Any members? Okay, wait, would you try?
Is a partial solution solving just for one? Like if you have multiple so you have like a y double prime and a y prime, and you're not solving to get a y equals, you're just solving for one like level. So you'll still have like you might solve for y prime, but you'll still have like a y double prime. You don't solve the whole thing. So y equals x, you might have like a y equals x y prime or something.
So one thing gives like general shape of possible solutions, scans through all possible solutions, and another is matching initial or boundary conditions. So which one is, I kind of remember, but I always mix which one is general, which is partial.
General, you should go back to initial conditions.
Yeah.
Which one for initial conditions?
General, I believe.
Okay, please check it and correct. I'm for some period of time I thought it's opposite, but
Or is it general in particular?
general in particular.
Oh, no, particular is going back to initial.
Okay,
Initial, like solving the whole thing, and then general is just getting the idea.
okay, yeah, thank you, Wyatt. Is it clear for everyone, or should I repeat after Wyatt, or after you repeat it again? You can just show secretly.
I was confused.
No,
You
you
said
did great. You can show me secretly, like, are you absolutely happy, absolutely unhappy, or don't care? You don't need to disclose it to others, but you can maybe show, keep your eyes open if you are okay, close both eyes if you hate it, and close one if you're halfway. So, then your peers will not see, and you will not see either. They will not see your glory or shame, whatever. So eyes open, everyone is okay.
No, please can you explain again? Because I'm not even sure that I understand what partial solution. I have no idea.
Okay, so there are two types of solutions for differential equations. One is showing general class of solutions which satisfies differential equation, but doesn't answer any practical problem. It's not useful for science or engineering. So it's mathematically correct, but absolutely useless for practical life. And another one, particular, addresses something specific that science and engineering is needing. And particular can be composed out of general. Better? About useless mathematicians. It's maybe not relevant, but a joke. So there is a thunderstorm, city, downtown of a small city, and a stranger with a dog is walking. Then suddenly there is a gust of wind and a balloon with travelers lands. The travelers, they're worrying because it's adverse weather, and they ask him, please help. This stranger asked, can you tell us where we are located? He stopped, thought for some time, and told, you are located on a balloon. And then the gust of wind removes the balloon. And then these two travelers talking to each other. I'm confident that person we met was a mathematician. How do you know? First, he was thinking before answering. Second, he gave absolutely correct answer. And third, the answer is absolutely useless. So general solutions are useless, and particular solutions are helpful. So if we take for any number n, the eigenstate of this Hamiltonian, the Schrödinger equation, and appropriate corresponding to it eigenvalue and multiply them, it will be general solution. Or if we add together all such pairs, phi sub n times exponential with depending on energies, and it will be a general solution. But it is useless. It doesn't help us to fulfill our goal to go from past to the future. And in order to go from past to the future, we do need to include these pairs, these products, with a specific weight coefficient, with specific percentage. So many percent of the solution number one, so many percent of solution number two, so many percent of solution number three. And if you find this percentage, then we go from this useless general solution to practically useful particular. So I'm going to develop a story in this direction, how to find this percentage. Okay, general useless solution. Can't read my own things. Scalar product. Okay. Oh, okay. I remember what I was talking about. So you can teach me this thing maybe better than I can tell it, but I remember at the beginning of our meeting, everyone was showing me the definition of orthogonality, right? So if it is two-dimensional vectors, it's just parallel or perpendicular, right? So how do we think about orthogonality for the functions? I have no doubts you understand. I just want to give an example. So if two functions coincide, if they're parallel, you just multiply function by itself, integrate, and if they were normalized, you will get one. If they were not normalized, you get something non-zero. If you take functions that are different and multiply them and integrate over the whole space, there is a very high chance that the result will be zero. Make sense? Absolutely disagree, or maybe yes, maybe no. Okay, thank you for showing this. This is a little counterintuitive, but let me show a very simple example. So suppose we have first simplest functions, just constant and linear. And then we want to multiply these functions and integrate it either from minus infinity to plus infinity or put more specific numbers. So integral of x is x squared over 2, right? And then if we explore it on the equal by value but opposite by sign limits, it will be x squared when we plug this over to this one minus the same value. Since square is positive, the result will be 0. So I'm not a mathematician, so I do not give a proof, but it's just an example of two functions that if they are not coinciding, their product gives 0. This property of orthogonality will be used. So I'm going to show a little derivation to prove that the third way of predicting future is correct. And if you refer to this property. And here is just a geometric way. So linear times constant will be area which is negative, area which is positive, and they cancel each other. And for example, if one does the same thing for sine and cosine and integrated, they will compensate each other and product will be 0. And with many function sets, it will be true. Okay. So nothing new here on this slide. So it's basically the same idea. If you want particular solution, we take summation of general solutions and multiply it by percentage. So the question is how to find this percentage, and or maybe if you would mathematicians, how to justify that certain equation for this percentage will be correct. And this percentage must depend on past, because our goal is to predict how to go from past to the future. I need to wipe it off because no one, including me, can read it. So here is the plan. And I think we need to discuss it before looking on the ugly slides. So the plan is as follows. First, we will just write down the functional form, the result as we want to see, as a summation of products with weight coefficients, where weight coefficients are unknown. And then we will plug it. We will make equality between our final wave function or initial wave function which we assume we know, and this expansion. And then by making equality between one function on one side and the sequence, a series of several functions with unknown coefficients on the other, we hopefully can solve for this unknown coefficients. Does it look reasonable or not quite? Reasonable, absolutely unreasonable, or more or less? Just repeat? Okay. So I do not have confidence that you either memorized or even agreed, but at least no one was protesting against this equation. So the particular solution is a summation of the general solution, so time-dependent part, and space-dependent part, where here's eigenfunction, here's eigenvalue, times percentage. Right? So it would be not right for me to say it is accepted by community, but at least no one was protesting. So it was silent justification. So now, if we plug in time equals 0, energy times time equals 0, this expansion, this set of added together functions must be equal by our initial conditions when time is 0. So on one hand, we have function which, well, by now I know nothing, but we assume that this function is known, past is known. And here, again, since we are doing board and abstract things, I also know nothing, but I assume that phi sub k is known, e sub k is known, 0 is known, but c sub k is not known. And by looking on this equation, I hope that I can do some manipulations to solve, to find exact values for this c sub k. And the idea behind it that we are speaking about the same thing. We are speaking about particular solution, wave function at time 0, either by looking on actual initial condition, wave function at time 0, or its representation by laws of differential equation theory. We should have them equal. But this expansion that comes from differential equations has sequence of unknown coefficients c sub k that we need to find. Better? Okay. And here is the plan how we are going to do. What is exponential of 0? 1, right? So we can completely remove it. So the black box is the same as the purple box, right? So psi x comma naught equals summation expansion coefficients times phi k. Now, I feel that I am challenged. I have only one equation and infinite number of unknowns. So how do I deal? I need to give like 100 answers, but I have only one equation. It's not fair to me. So I need to do something to convert this one equation into like as many equations as I need these answers. And here the plan is to use this orthogonality relation. The fact that wave functions will be either parallel or orthogonal. So in math, although we are not mathematicians, there is a common trick that helps very often. So if you have equation, nothing will change if we add the same term to both sides, and nothing will change if you multiply both sides by the same factor, right? Especially if you do not violate commutation, if you like multiply it from left or from right simultaneously, nothing will change. And I think this is the main mathematical idea that we will use through the course, and I think in many derivations. You just plug in additional factor wherever it is reasonable. So what if I multiply left and right part by another eigenfunction for the same Hamiltonian, but with different index? Like if here it was phi k, here I would do phi m. And I would put little stars that will be conjugated just in case. So I hope when I flip the slides, there will be more equations, but here is the idea why this trick should help. If in addition to multiplying, I would add integration, right, in the left and right, then on the right side, I will have integration of phi sub m and phi sub k from minus to plus infinity. Yes? And this integration is a way to remove functions and convert them into a number. So by performing this product and then integrating it, it will give me either 0 or 1. And this 0 or 1 will be different each time, depending on what are the values of this m and k. So I hope very much that this trick will help me to convert one equation into a series of equations that will help to find for this C sub k. Make sense? Okay. Yeah, I probably intentionally left slides to scratch things, but maybe we'll skip this exhausting exercise of calligraphy. You saw that I'm not perfect at it. So we multiply not just by function with different index, but by function integrated over dx from minus to plus infinity on the left and right side. Then we have this bottom box is absolutely the same. I just type it in continually. So integral phi sub n, then psi, which is the initial condition, then integral phi sub n times this expansion. So what do I want to do? I want to, if we do not have differential operators, and if you have only numbers and functions, one can swap the order. And integrations and summation are also swappable. So if I put summation C sub k at the front and integration right here, nothing will be wrong. And here it is not cross product. I just was it's also only space separation of the symbols, so it will be confused. So I'm going to swap this thing, and then this integral with this function will be a way to practice orthogonality, to check if they are parallel or perpendicular. So let me introduce PChem class of 2021. Here is the Chronicle delta. Chronicle delta. Here is the Pickham class of 2021. Have you seen this symbol before? Let me show. Have you seen the symbol? No. So it's just an abbreviation because here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 symbols, and here is just 1, 2, 3. But it's just abbreviation of this bracket and telling that it is 1 when indices coincide and 0 when they do not coincide. Better to write is not equal to n. K is not equal to n. It's not only I have no excuses, but one of my excuses that when you try to use this touchpad, you place your pen in one point and it make marking like 1 inch away. So there is nothing new, it's just a notation. But if you write long equations, this notation will help just to be concise. So we did swap order. We have in the right part we have summation and then this integral, right? And this integral we completely are justified to replace it by this Chronicle delta, telling that this dashed box will be 1 if this indices coincide, if it is the same eigenfunction, it will be 0 if they are orthogonal. Right? Do I need to vote for your approval of this step? Okay, yes, thank you. Okay, now maybe I do not have time to draw it over. No, I will. It's my favorite part, and I like my teacher who did show it to me in my undergraduate classes. So sometimes, if you do boring derivations of equations, you see situations where the summation symbol and delta and k symbol are found together. So what should we do? Is there a way to simplify? Yes, there is. And it's not possible to concentrate on all equations when you sit in class. There are many important things in life. There is a wish to just sleep a little. There is it's all normal. But I'm going to tell something that woke me up, like when I was in the similar class sitting and was about to fall asleep and skip this long equation. So the Chronicle delta can be thought either as a mouse with a tail. I'm not a good drawer. Or maybe students from previous years told me to think about as a mouse. I was thinking about it as a rabbit. It's like 2 ears. So some small rodent. And the summation sign can be thought as angry snake with tooth. So when this summation sign find this mouse or this rabbit, it eats it. And basically, as a result, they both disappear. So these two strange symbols can be cancelled with very little price for it. Okay, so how to justify it? So I'm going to tell a story about this mouse and snake in a little bit more abstract way. So summation and canonical delta. If I have nothing to do rather than write equations, which is typically not when I'm sitting in the class, but suppose I want to open it. So summation means I plug in different values, like 1, 2, 3, 4, 5. So letter K is replaced by numbers, and letter N is not. So it means I do have the values delta 1 and delta 2 and delta n, delta maybe some other n, right? So summation of this delta functions with first index being rhyme, taking different values. But now I do know that if these two numbers do not coincide, then it converts into 0. If it does not coincide, it converts to 0. If it does not coincide, it converts to 0. If it does coincide, then it converts to 1. Right? So this thing is converted to 0 plus 0 plus 0 plus 1 plus 0. So the result will be 1 for sure. Now, if I practice the same exercise with a little thing in between. So it will be 0, 0, and instead of 1, it will be 1 times the coefficient C multiplied the appropriate number. And then again 0, 0, 0. And then result of summation will be 0 plus 0 plus C sub n plus 0. So this equation parses one number out of a string. It parses one number out of a string. Yes, no, or not quite. Everyone is okay? Okay, yeah. If someone would be not comfortable, I have another argument for it. This can be considered, but let's not use it. Okay, so you agree that you parse only one number out of string. Now let's return to our equation. On left side, we had eigenfunction times past. On the right side, we got summation of this unknown expansion coefficients times delta function. But because of the rabbit and snake, we replace it just by one number, because this equation parses only one C sub k. Yes? And I think it is a win. If people celebrate mathematical derivations, it's time to celebrate. So before I had one equation and many unknowns. After this step, I have as many equations, as many eigenfunctions, as many expansion coefficients. So for each number n, I have a rule to find it. So basically for number n, I take eigenfunction number n, multiply it by past and integrate. Do I have approval for this step? Or everyone? Do I need to speak more? No? Maybe? Or so you confirm. So we do have a protocol to find this percentage, or colloquially one often calls it expansion coefficient. So then we do have expansion coefficient as a convolution of eigenfunction and initial condition. And then we can plug this expansion coefficient into our general solution and obtain particular solution. which will be the future for any time. So you can predict future at any time t based on knowledge of the past at time 0. If we do know eigenfunctions and eigen should be E, eigen averages. No, here is the letter K. Whew. Basically, we are done. Here is the protocol. We are getting from past to the future. And this completes the 3 ways to predict future in quantum theory. Done. Thank you for staying here. I think we are we are in time. So looking forward to see you on Wednesday, same place, same time, and have a nice Monday and Tuesday. I'll stay here and answer questions if any, but meeting is dismissed. Adjourn is announced.